Hello everyone, my name is Brad and I work for Geosoft and I'm glad you've joined us for today's webinar. It's entitled Integrating Potential Field Data with Seismic Data and Structural Geology. John Watson from Bridgeporth will be presenting, and he'll be presenting for 30 minutes, and it will be followed by a short question and answer period. So I do want to encourage you, as you think of questions during the seminar, to enter them there, and at the end of the seminar John will review those questions and answer as best he can, as many as he can. All right, we have lots of folks in the room today. Let me begin with a brief introduction. Potential field data is, well, it's often considered a seismic's little brother in oil and gas exploration. And in today's talk, it was originally presented at the EAGE 2014 conference. John Watson, he's going to attempt to show that with proper integration, presenting the data in a meaningful way, and importantly, at the correct stage in the exploration timeline, gravity and magnetic data can add significant uplift to the geological understanding. Now, I'd like to introduce our presenter just to give you some context for Jonathan Watson. Jonathan is the interpretation manager at Bridgeporth. He has extensive experience in acquisition, processing, and interpretation of potential field data within the oil and gas industry. Now, Jonathan has worked for over 15 years within the industry. He's starting as a processor and then moving into interpretation and then becoming a team leader of an interpretation department at an airborne acquisition company. He has worked predominantly in gravity and magnetics, particularly in its integration with seismic data, and has experience in working internationally in all geological settings. Well, thank you for joining us today, Jonathan.
Okay, as Brad said, I gave this talk a month or so ago at EAGE in Amsterdam. It's a relatively short talk, it's not particularly technical, and the title of it being Integrating Potential Field Data with Seismic Data and Structural Geology. In terms of the content of the talk, some of the issues I'd like to cover would be kind of historically how gravity magnetics has been used, and in terms of that, sort of examples of maybe non-integration and where it hasn't been used as well as it could have been. And then moving on to the present day in terms of the data available these days, and also how that integration can take place and its benefits. I'll look at the advantage and the use of potential field data in seismic planning. It's one of the key areas in which it's used at the moment, particularly in frontier areas such as Africa. And then look at some examples of where it's been used to help with sort of mapping structural geology, and how you can combine the data sets and get an integrated approach. A quick look at magnetic data as well. Generally, gravity is I guess the main potential field data set, particularly in the hydrocarbon oil and gas industry, but magnetics certainly has its place. I'll jump over then to geochemical integration, just as an example of where another data set can be applied and how that can all help increase your knowledge of an area. And then finally some conclusion slides. As Brad mentioned earlier, I guess seismic, potential field data is generally regarded as the lesser data set, or the less important data set, certainly within oil and gas companies. Seismic is king. However, airborne survey in particular has had significant success lately, particularly in frontier areas, so onshore Africa, the rift environment in particular. But integration of all these data sets is key. So historically, I think it's fair to say gravity data has been generally seen as a regional tool. And another comment or another observation I've seen whilst working in the industry is generally there's limited experience of potential field data within all companies. That's not always true, but to a large part people may have covered potential field data at some point at university, but once they've gone into the all-company environment, they may not get that much exposure to it. And with potential field data, there's always a question of non-uniqueness and therefore the uncertainty in it. And what I'm kind of mean by that in a very simple model is if you take two different geological scenarios, whether in this case it be a kind of a fault or an anticlinal feature, they can generate similar looking gravity responses. And what I'm hoping to show here is with a bit of extra constraint, a bit of pre-knowledge of the geological environment, and with a bit of common sense, a lot of that non-uniqueness can be removed, and both an integrated and a confident model can be produced. So why is it so underused? Well, I've put together a couple of statements here, and this is a lot of what I hear if I'm going in to speak with oil companies, is that they've acquired the Gravimag data, but they haven't done much with it. Now, whether that's a lack of understanding, and they don't understand how useful it can be for the exploration, or timing. I mean, quite often we hear, yeah, it sounds good, but they're on a tight timeline, and they don't really have the time to really apply it as best they should. And so I've said we need, and by we I mean really the consultants, the contractors who specialise in potential field, effectively try and become more part of that exploration team, and that allows us to deliver results both alongside and integrated with that exploration program. In my experiences, it works best when you deliver a project that the client has had involvement with from the very beginning, rather than maybe producing a final potential field project or a report that is delivered at the very end or without little interaction with the client. And also another issue I guess we come across in potential fields is that we generate in some instances what we call geophysical models rather than geological models. And I think it's important when we produce our results to present something that's meaningful to an oil company geologist. As I said, they may not understand exactly the methods and the sort of first principle techniques, but if they are delivered with something that they understand how it's got to that point and that is useful to them, so they can load it into a seismic package that they're using, etc., then that's an important role. And finally, I guess data that's not explained properly can be considered misunderstood or even not of any use. I've got a couple of examples here of what I would guess call non-integrated data. Here we've got some simple magnetic modelling, and this is perfectly reasonable. It's just a way of representing a magnetic body and then modelling that accordingly. But I guess it lacks, once it's a geophysical model, it lacks that geological input. And I'd argue that the best way to present these, particularly to oil companies and geologists, is to tie that in with some geology and make it a bit more realistic. And another example where, for instance, magnetic data is very useful for generating depth estimates to depth to sources, whether that be volcanics, basement, whatever. And again, what we've got here is a display showing a whole series of depth estimates. There's actually a lot of useful information, but I'd argue that maybe it can be presented in a better way. So maybe grid those points up, produce a surface, because then that's something that can be taken directly into a seismic package, and it is more meaningful to an oil company person. So we move on to the present day. Modern acquisition techniques certainly allow very high resolution data sets to be acquired, and certainly one of the advantages is the ability to cover large areas quickly and cheaply, and this is ideal for frontier areas such as Africa. And my final point there, I guess, is that arguably you can say that the data is not the issue. The guys that are acquiring the data are, on the whole, acquiring very good quality, high resolution data. It's that integration that is the key part. And a couple of examples of this. Here's some FTG or gravity gradiometry data acquired by Bell Geospace, and this is over a relatively small area. And hopefully you can see that there's a a lot of real geological information that's within that data set, and it's certainly not regional by any means. And it's a way of the key really is to then integrate that data and come up with a meaningful interpretation of it. And here we've got another example of some magnetic data and how that magnetic data can help you with, in those three examples, intrusions and grabens, bedding and structure, and extrusions and alteration. So there's a lot of information there. So I've got a couple of examples where I'd argue that it has been used correctly and you get meaningful results. So here we have a gravity data set onshore Namibia. And if you take that data set and come up with arguably a sort of geological 2D model that has the faults in, has the basement structure in, has the right lithology and sort of units in place, it just makes more sense and can be understood very easily to a geologist. And then moving from 2D to 3D, again we have an example here of a depth to basement surface that was derived through gravity and magnetics in the UK in the Central Graben North Sea. And again, by combining it with the seismic data, presenting it as a surface, it's a really useful product. So in terms of integration with seismic data, gravity and magnetics is often a precursor for seismic acquisition. Again, I could keep referring back to Africa, but certainly there's been a lot of activity in terms of airborne acquisition in Africa of late. And it's particularly suited for these large frontier areas. Logistically and security-wise, the issues of establishing a large seismic crew in country are difficult. So being able to go in there with a small team relatively quickly and relatively easily and acquire a large or broad data set of potential field data that then can be used to help with the seismic planning, I think is a very important role. And I'd argue that certainly with some of the clients I speak to these days, is that ability to help with the seismic planning and from both the cost and logistics point of view is as important as the final delivered interpretation results that come through. And it's difficult to put a cost on it, but I've included there that you could argue that the typical gravity magnetic airborne survey could be the cost equivalent of only 70 kilometers of land seismic. I've got an example of how that could work. On the left there we have a typical seismic program that may have been put together without much information, so maybe a few geological maps, maybe some public domain data that was available that results in a relatively uniform, regular seismic spacing. And the argument would be, if you'd already acquired that potential field data prior to the seismic, would you still acquire that same seismic pattern? And then on the map on the bottom right now, that's the same line kilometrages of seismic data, but arguably placed in a better orientation and a better positions to target what appear to be interesting looking structures from the potential field data. So moving on to more of the interpretation side and how you can integrate that with seismic data and kind of the structural understanding. We'll take a seismic section here from East Africa, and you can see generally that there's, hopefully this is a kind of standard basin with the bounding faults on either side of that line and then some kind of structural high in the center. If we display gravity data acquired along that profile, you can see that overall the gravity is in agreement with that seismic, showing effectively the basinal areas. But I think one of the issues I find with clients is to get them to understand that there's certainly much more information that can be derived from this data than that kind of simple model. If we apply, so just very simply, if you just pick the kind of the rough edges of this basement, you get to see the the orientations kind of line up and it's all in agreement. And you can draw in a rough basement interpretation. So from there, the ability to filter the data or to apply some kind of derivative transform allows you to extract a bit more information and a bit more structure effectively from that line. So with that filter in place, you can map some extra features, some extra trends and structures, and you can refine that basement and get a more detailed, better looking basement structure. And then effectively you can do the same thing again and you push the data as really as well as it is resolution or its survey parameters allow. And again, refine the basement again. So from that initial model showing just a general basinal area flanked by basin high on either side, you can get to quite a detailed peak of basement structure. And again, that's very useful going forward in the exploration program. Another example we've got here is example where there's sort of limited surface geology, with obviously in the centre there a relatively widespread uniform surface cover. So the information of what's going on underneath that is difficult to establish. If you bring gravity data over that area, you suddenly see there's a lot of structure that was not apparent with that surface mapping. And with the potential field data, arguably what you're able to do is go out and pull out those lineaments, those what appear to be faults, offsets, etc., and build quite a comprehensive structure map, surface map, if you like, that both ties into the surface geology and also gives you an indication of what's going on underneath. Just another example really of that process, but with a different setting. Here we have a thrust area that's been mapped to a reasonable or relatively simple standard really in terms of picking out the main thrust, the main offsets, lateral ramps, etc. If we overlay, this is actually some FDG data that was acquired over this area, and what you see with those red features on the FDG is the anticlinal features of thrust fronts. And hopefully you can see that there's a lot more information in that data set than is in that initial interpretation map. So what we're able to do is go through and firstly map the main features and show how they sit with the previous interpretation, and in some areas it fits very well, so it gives agreement to what they see. In other areas it's not so good. Now whether that's due to the seismic data in those areas is poor and there's a lack of understanding, or just a lack of resolution in the seismic data and not the ability to join from line to line, which you have with the potential field data. And this was effectively the final map we came up with for this area, showing the main thrusts, the main offsets, and also minor thrusts, minor offsets, and then also the anticlinal and synclinal features. And this was quite an improvement on that initial map. I'll go to magnetic data now. I guess certainly on the projects I've worked on over lately, it's the gravity that's the dominant or the more prominently considered useful data set. But you know, magnetic data is often acquired alongside, particularly in airborne surveys, alongside gravity data, and it does offer a lot of information. Here we have an example of a magnetic analytic signal map, which is I find a very useful map in mapping sort of particularly lateral extents of volcanics, and particularly kind of shallow intrusives in certainly in cases where you may have a deeper basinal area but then has intrusives within it. This can be a useful data set to help with understanding of that. Then moving on from potential field data, I always wanted to cover geochemical data. Now, in a very simple way, you could argue that surface geochemical data can indicate a working petroleum system, but doesn't really give you any indication of size and extent. The potential field data can indicate basinal areas, but then it's not a direct indication of a hydrocarbon producing system. So ideally, a combination of both the gravity magnetics, the seismic and the geochemical can hopefully produce an integrated model. And particularly in frontier areas, the establishment of a working system is key for companies, whether they're looking for further exploration funding or farmings or CPRs. It all helps to build a case for a good potential exploration target. And here we have, going back to that thrust area, this was a surface or depth surface map we produced, effectively showing the anticlinal features through the area. And then the symbols on there are actually surface seeps that have been recorded historically. And there was quite a nice correlation between the two. So it was quite an interesting result to see where the oil seeps and the potential structures lie. Yeah, okay, that's brought us on to the conclusions, really. So to summarise, I would say nowadays the data that's been acquired is of high resolution, and it's the interpretation that is the key to giving a well-delivered, well-constrained data set and product. And then it's that integration, whether it be integration of data, seismic data, geochemical data, and also integration of the people involved is key. I'd also argue that producing geological maps and deliverables that are meaningful to the client, and also in terms of timing, critical to the exploration process is important. And that, again, it's not just the gravity data, there's the magnetics, there's geochemical, there's also other airborne techniques or other geophysical techniques such as hyperspectral imaging, gamma ray, and more of the minerals exploration tools that can all add this extra information. It's the ability to pull it all together that is of, that I guess is of key interest. Okay, I'm hoping that that all went reasonably smoothly. Brad?
And John's just reviewing the questions right now. And if you would mind just letting us know. Very good. Go ahead, John.
Yeah, I'll read it out first. Yep, that's fine.
Very good.
The question is the gravity-derived, oh, hang on, they're moving now. Right, is the gravity-derived structural mapping done automatically or by a geological interpreter? I tend to use both approaches. Certainly as a quick first pass, using the automated edge detection tools is a good way of pulling out lineaments and trends and features. And then whether you apply that to kind of residual or filtered gravity data or horizontal gradients, I think you can build up certainly a relatively quickly a decent set of results from that. But I think it's important to then use those results, compare it against seismic data, compare it against other information, and effectively come up with more of a manual interpretation that may not include all the detail that the automated results pick, but makes it a little bit more meaningful in terms of the targets and the structures that you're interested in. Okay, so I'm just going to look through some other questions now. Yeah, there's a slide I showed in the question, is in the slide where the basement was drawn and refined over the top of the seismic data, there were two traces, red and green, that seem to have higher frequencies. What were those traces? And the question is derivatives. And yeah, what those traces were effectively high pass filtered the gravity traces. So just by applying different filters and targeting different wavelengths and effectively different size structures and depths, that's what those traces represented. Just looking through some more questions. Okay, there's a relatively simple question here. Is what? I'm not sure it is what or how can grav and magnetic data help in the case of salt dome areas? I think greatly is a simple answer to that. You know, gravity and to some extent magnetics has been routinely used in areas of salt, whether it be offshore Gulf of Mexico, offshore Angola, Gabon, North Sea, onshore, well, various, again, onshore US, Poland, wherever really. I mean, because it's such a strong density contrast usually with the surrounding sediment, then it does work very, very well in salt environments. Okay. Sorry, I'm just reading through the questions. I've not.
Yeah, by all means, there's lots of questions there.
Yeah.
Great questions, everyone. Thanks for participating. And great to see your answers to that poll. Very interesting.
Okay. Okay. There's one is how do you integrate well log data into your modelling workflow? Well, if you have a density log is certainly a key part of the workflow if it's available. Being able to back out both from the well logs some, if you like, average interval velocities and also average interval densities for help with the effectively both the time depth conversion and the parameters of the bodies themselves. It is very useful. As I said at the beginning, the more data that you can throw at it, the better. So if you have well information that can be used, then yeah, integrate it. Hang on, I'm just... Okay, there's a question here saying, I find magnetic modelling challenging. I'll need a guide to overcome the challenge. I would certainly say that gravity is generally an easier data set to interpret. It tends to be simpler in the fact that if you have a gravity high, you're looking at a dense, a denser body, whereas a gravity low is effectively a lighter body. Whereas magnetics, because of the factors such as the inclination, declination of the field where you're acquiring the data, the magnetic remnants, and so forth, it's not as an easy data set to interpret, and certainly someone with limited experience looking at gravity map could probably generate some reasonably sensible results from it. Whereas magnetics, you could certainly, if you weren't exactly sure what you're looking at or how to interpret it, you could make some, or fall into some kind of pitfalls of interpretations of mag data. And certainly in terms of where to look, there's I can't think off the top of my head, but there's certainly the general textbooks, Telford, etc., go into detail in terms of understanding magnetic anomalies, etc. Okay, there's a question here on how reliable has the integration of surface geochemical data been in your experience. It's not something, it really depends on the area you're working in, and quite often, particularly in frontier areas, you don't have that information anyway. The example I showed appeared to work quite well, but it was a very simple result of just plotting the locations of those seeps onto the maps we produced. There wasn't any real further integration done. That's not to say that there shouldn't be or that there won't be in the future. It just at the time of the project that was as far as we pushed that. It's more of an observational result rather than any detailed work. There's a sort of a general question saying, how about using potential field data with poor quality seismic data and with a little geological info? I guess the question is this a valid way to use it? And effectively, yeah. I mean, seismic data certainly within the oil companies it's the more expensive, it's the more seems to be the more important, useful data set. And when it works well, yeah, it's a great data set to use. But certainly, there's plenty of both from a acquisition parameter and a geological problems that mean the quality of the seismic data derived can be poor. So yeah, there's certainly using potential field data or any other data to help constrain that.
Bear with us 1 minute. I think John's having some audio difficulties. John, we're not able to hear you. There we go. Now you're back. Sorry, John,
Sorry.
you dropped out there for
Okay,
about 20
right.
seconds.
Okay, apologies. All right. I'll probably. I wasn't. There's a lot of questions coming through now, but some of them are quite specific. So what I'll probably do, if there's no problem, is kind of leave it there for the moment, and then I guess I'll get a copy of these questions and who sent them. Anyway, is that right?
Yes, you will, John. Yeah.
Okay.
I think that's a great way to do that. We'll compile all these questions. You have so many questions here, great specific questions.
Yeah,
We'll
okay,
let John
yeah.
answer them. We'll put it together in a document and actually provide it with the recording, a link to the document and John's comments and his answers to the questions.
Yeah, okay. I'm not sure I'll be able to answer all of them, but I'll.
Well, the ones you can, yeah.
Yeah, sure.
Yeah, very good. Anything else you want to add, John, before we wrap up today's session?
No, just thanks for people listening. I hope it was of use. As I said, it was a relatively simple kind of overview, really. But yeah, as I said, hopefully it seems to have raised some interest and some questions anyway. So thanks very much, Brad, for organising it, and yeah, thanks for all attending.
Very good. Well, on behalf of Geosoft, John, thank you so much for joining us and taking time out of your day to present this talk again. The global exploration community really appreciates your time and your expertise in all of this. And just a reminder to everybody who's attended or had to leave that the recording of today's session and those questions and those answers will be available once we edit the video and compile all those questions. All right, everyone, have a great day. Take care.